Like with side 0 and side 1.
Sorry, I'm not paying attention to you because I'm having a problem in the recording. Let me fix this and then I'll. I think it's picking up from somewhere else. Let's see how it works. Okay, yeah. What was your question?
With tau equals 1, with theta equals 0.
The boundary condition?
Yeah.
Yeah. I'm going to talk about it. If there are no questions about your assignment or feedback from Esther, I do need feedback because if you find that we could restructure the tutorial in a different way, I'm willing to listen to it. Okay. So yesterday I just brought a few examples and I said, well, let's write the program together, and that way you see the whole process of making mistakes, correcting mistakes, and trying to get it to work for a given problem. So there are no feedbacks. That is my intention. I want to build on that kind of problem solving in the next 3 or 4 lectures, introducing different features of MATLAB as we go along. But if you request that I need help with arrays, or I need help with function, or I need help with passing variables from one function to another function, let me know and I will set up some examples, make up some examples to drive home those points. You can send me email. Okay, just say, Kumar, I would like you to cover this in the tutorial, and I will try to make up something like that. Okay. In the last lecture, we were looking at many things. It was a heavy lecture, come to think of it. And what we did was how to build a model from a heat transfer course that results in a distributed but steady state system. Okay, so that results in an ordinary differential equation, but it is called the boundary value type. And you should understand why it is called the boundary value type, because the conditions, a second order equation will need 2 conditions. If all the 2 conditions are given at the same location, typically t equal to 0, and t is the independent variable, then you get initial value problem. And we have seen how to solve that in the previous 2 lectures. This week we are focusing on boundary value problems. Again, we end up with a second order differential equation. Now the independent variable has the meaning of spatial variation, something that varies in space, but it is steady. It's not varying in time. And the example that we saw was the fin. Okay, so when we developed the temperature profile in a fin, we ended up with a second order ordinary differential equation with 2 conditions at 2 different ends, the base of the fin and the tip of the fin. That's why it's called the boundary value problem. There is a finite boundary and you give conditions at both ends of the boundary. And then the second important thing that we saw is how to put that into a dimensionless form, okay, by defining dimensionless variables. And so we ended up with an equation like this, where theta is dimensionless temperature. Dimensionless meaning it has no units, because both numerator and denominator have temperature, so they cancel out. Theta has no units. Similarly, psi is a dimensionless distance, and it has no units, because x is the distance, has the units of meters or feet, and L is the same thing, distance measured in terms of that. So the nice thing about this definition is theta will always go between 0 and 1, and psi will always go between 0 and 1. So you have a very nicely scaled problem. I have a question for you. Okay, after we went through that, we ended up with an equation like this. Now we have a grouping of various parameters that appear in this problem. H is the heat transfer coefficient, P is the perimeter, L is the length, and K is the thermal conductivity, and A is the cross-sectional area, and we are looking at uniform cross-section in this particular case. And each has different units. Okay, K has units of watts per meter degree C, H has the units of watts per meter square degree C, L has the units of meter, A has the units of meter square. What should be the units of this entire group? Very good. It should be dimensionless. Why? Everything else in this equation is dimensionless. Okay. If this term is dimensionless, this term is dimensionless. So this whole thing has no units. That means every term in such an equation should have no units. Okay, so you can check this. You can plug in the numbers for the units for h and k and p. You will find that it is dimensionless. This is how dimensionless groups are born in some sense. Okay, in fluid mechanics, you will come across a lot of dimensionless groups: Reynolds number, Prandtl number, Schmidt number, things like that. These are all dimensionless groups that they represent a ratio of two physically meaningful quantities. And with that dimension number is 1, for example, this says that both the mechanisms are about the same order of magnitude. They are equally important. For example, if we call this as m, if m is equal to 1, what is the physical meaning that we can attach to it? Well, the numerator has h. What does h stand for? Convective heat transfer. That is the rate of heat loss from the fin surface to the air. Okay. In the denominator, we have k. What does k represent? Conductive heat transfer from the base of the fin to the tip of the fin. Remember, this picture you should have in mind. This is the fin that we are talking about, and the base of the temperature is at 1, and the tip could be at 0, or I could have d theta d psi as equal to 0. What are the two conditions at the tip? So the heat is being conducted in this direction, and that is my dimensionless distance psi, which always goes between 0 and 1. Okay, and the temperature will also go between 0 and 1. I scaled it. Okay, so this dimensionless group represents a ratio of the rate of convective heat transfer to the rate of conductive heat transfer. If it is of order 1, then you have a good design because you are matching these two mechanisms. If it is too small, that means your convective heat transfer is inefficient. You are not removing heat from the fin to the surrounding as efficiently as heat is delivered to that point by conduction. Okay, they match, then the rate at which heat comes into that particular point is equal to the rate at which it leaves. Okay, so dimensionless groups are very important in chemical engineering, and you will see them in all the courses that you do: fluid mechanics, heat transfer, mass transfer, reaction engineering, etc. Because they express two competing forces, the ratio of two competing forces, and in design, that is the only thing that you need to worry about. If you're designing a fin such that this is of order 1, then you have a reasonably good design that is matching very well. Okay, any questions on that concept? Absolute silence is not good. Is it okay? All right. So this course is many things. This course about fluid mechanics, heat transfer, mass transfer. How do we model systems? How do we interpret results? It is also about formulating the model, analyzing the results, learning how to solve it in MATLAB. Okay, so the agenda is quite big indeed. And the other important thing that we saw in the last lecture is how to convert a higher order differential equation into a system of first order equations, equivalent system of first order equations. That means converting the equation and the boundary conditions to a consistent set. Why do we need to do that? That's a good question. The reason is MATLAB and most of the other software that are available will handle only systems of first order equations. Okay? If you want to write your own code, then you can write it for a second order code. But because these are standardized packages that are meant to solve a wide variety of problems. I'm giving you this as only an example. Whenever you have a boundary value problem in any course, you should be able to go to that routine BVP4C and set it up to solve. But you need to learn how to set it up. That means you need to learn how to convert a higher order system into an equivalent set of first order equations. And we saw how to do that for the fin problem. Okay, we ended up having two first order equations that you see here. Okay, and the first function f1 is simply y2, and the second function f2 is m times y1. These are the two functions that you need to write. You need to write a MATLAB function, m5, and pass it to the solver, boundary value solver, indicating these are the two functions because they specify the problem. And then you need to also specify the boundary conditions. The boundary conditions are y1 at psi equal to 0 is 1, y2 at psi equal to 1 is 0. The reason it is called a boundary value problem is they are at different locations. Two different conditions at two different locations. If both were given at psi equal to 0, then you will treat it as an initial value problem and use ODE 4.5, ODE 1.5, etc., which we saw in the last week. Okay. Now what we are going to do in this lecture, before I get into MATLAB, I want to complete and ask you whether you have completed it, before we read and try to interpret this, because that is also a skill that you need to learn. In MATLAB, as I said, what I know about MATLAB is probably 1 or 2%. It's such a huge package. But what is important is for you to be able to read the help file and make sense out of it so that you can set up the problem in future on your own as you deal with other problems. I think I'm going to have some problem today in lecturing. There's something, recording the lecture. Something funny is happening. All right. Let's go to that particular problem that I posed last lecture at the end and ask you, because this is an important step that you need to be able to do before you can solve it in MATLAB. This is something I will test you in the exam as well. So I just made up a problem, a third order ordinary differential equation with 3 conditions. One is at psi equal to 0, one is at psi equal to 1, the other one is at psi equal to 0. The first one is for theta itself, the second one is also for theta, the third one is for the derivative of theta. And I wanted you to convert that into a system of 3 first order equations that you see here. So that means there must be 3 variables in a vector that you define y. They contain y1, y2, y3. And what you need is dy1 d psi equals f1, dy2 d psi equals f2, and dy3 d psi equals f3. And the question is, what are these f1, f2, f3 such that this representation is the same as the one that is given? And you also need to find the boundary conditions for this y1, y2, and y3. So we are defining 3 variables, and we are trying to define it in such a way that when I solve it, I will get the solution to theta as a function of psi. What I need is theta as a function of psi. I need to generate a graph of theta and psi between the limits of 0 and 1 in psi. So I need to have a curve like that. That curve should, when I plug it into the differential equation, should satisfy the differential equation. When I plug it into the boundary condition, it should satisfy the boundary condition. What does that mean? It means at this end it should be 1, at the other end it should be 0, so that curve is obviously not going to do that, and its derivative should also be 0. Okay? So what is the recipe? The recipe is define y1, y2, y3 in a particular way. Okay? So that is a definition. Okay, so we're going to let y1 be equal to theta. So I'm really interested only in y1. y2 and y3 I don't care, but I need to solve them as part of the package. Okay? So y1 is theta. If I know y1 as a function of psi, I have solved the problem. Then I'm going to let y2 as equal to d theta d psi, the first derivative, and y3 as equal to d squared theta d psi squared, the second derivative. This is where I stop because I know I have third order equation, so the 3 variables are defined as simply the function, its first derivative and second derivative. Now I need to formulate the 3 equations. So in order to do that, I'm going to take the derivative of the first variable. Okay? So I'm going to take dy1 d psi. When I take the derivative of that, on the right hand side I have d theta d psi. Okay? So that is the same as d theta d psi. But d theta d psi from the second equation is the same as y2. So you set that equal to y2. That is your first function. So the first function is simply y2. It's not a complicated function. It's a linear function. Okay? You do the same thing with the second variable. Start with the second variable and take its derivative, dy2 d psi is equal to d squared theta d psi squared. That is, I'm taking the derivative of the second equation on both sides. And then I say, okay, what is d squared theta d psi squared? It's just y3. So that gives me my f2. So I found out f1, I found out f2. Okay? So I have 2 equations I already know. dy1 d psi equals y2 and dy2 d psi is equal to y3. I need to find the third equation. So this is the third equation that the original equation will enter. Okay? Because what I'm going to do is the same thing. Take the derivative of dy3 d psi. That is going to be equal to d cubed theta d psi cube. But then to get that third derivative, I'm going to look at the equation that I have, because there I have the third derivative. So isolate the third derivative on the left-hand side, move everything to the right-hand side. As you move them, you substitute for theta, d psi, d square theta, d psi squared in terms of y1, y2, and y3. So the first thing, minus theta squared. Okay. So what is theta? Okay, let me just maybe write it first and then substitute it. Minus theta squared minus 3 d theta d psi minus 5 d square theta d psi squared. Okay, divided by the whole thing divided by 10. That is my third equation. dy3 d psi equals the right hand side. That is going to be my third function f3. But I don't want the higher derivatives. I want first order systems. So what I'm going to do is substitute for theta. It's going to be minus y1 squared minus 3 times, what is d theta d psi? y2. Minus 5 times d square theta d psi squared is y3 divided by 10. That is my third function f3. So you will write an M file that takes as input y1, y2, y3 and sends out as output f1, f2, f3 according to this definition. And then MATLAB will be able to use that function to solve this particular problem. Okay? That is the process of converting a higher order system into a system of first order equations. The number of equations you will end up with is the same as the highest order in the differential equation. Any questions? Yeah?
The y1 squared, isn't it actually...
Good question. So I was going to ask you, is it a linear or a nonlinear problem? In the first equation, you have dy1 d psi equals y2. There is no product of y1, y2, or y3. There is no square. There is no exponential. So the first equation looks linear. The second equation, same thing. dy2 d psi equals y3. Okay? There is this equation. Looks linear. But in the third equation, as you observe, y1 square is a nonlinear term. y1 times y1, product of y1 itself. So if you have y1 times y2, it will still be nonlinear. Okay? So, and then the next two terms are linear terms, but all you need is nonlinearity in one place, anywhere in the system. It makes the whole system nonlinear. So this is a nonlinear equation. If your question is, does it pose a problem? The answer is no. MATLAB will be able to integrate linear or nonlinear problems within the same solver, within the same framework. Whereas if you're trying to do it analytically, it's impossible to do it for nonlinear problems. So that much you should be able to identify. In an exam, after developing this, the standard questions will be, is it lumped or distributed? Is it steady state or dynamic? Is it linear or nonlinear? Because that classification is the one that's going to guide you to the right tool in MATLAB. Okay? So you should be able to identify it is nonlinear and where is the nonlinear term. Any questions? How do we do the boundary condition? Now I have 3 first order equations. I need 3 conditions. The conditions were given in terms of theta at 0, theta at 1, and d theta d psi at 1. So all you have to do is write them in terms of the new variables. So what would be those conditions? Theta is the same as y1, so that condition there will become y1 at psi equal to 0 is 1. Then you look at the next boundary condition. Theta at psi equal to 1 is 0. Theta is still y1. Okay, so it will be y1 at psi equal to 1 is 0. It's a third one that you need to be careful. What is the third condition? D theta d psi. y2. Okay. The third, it's d theta d psi is defined to be y2. So y2 at psi equal to 0 is 0. Okay. y2 at psi equal to 0 is 0. Now I have all the boundary conditions. I have all the 3 functions. I can go into MATLAB and define them. Let's go into MATLAB and go and solve the fin problem. Not this problem, but the fin problem. Okay, so far I have identified the problem to be the fin problem. We already discussed it, whether it is linear or nonlinear. We identified it is a linear two first order equations, and we know what the functions f1 and f2 are. We know what the boundary conditions are. It is this information and this information that we need to pass, that you have here. These two have to be passed in a very specific form for the MATLAB function to understand and solve this. And what MATLAB will tell us is this is the temperature profile. The temperature profile might look like, it will give you a graph of theta versus psi going between 0 and 1, 0 and 1. It might give you a graph like this, or it might give you a graph like that, or it might give you a graph like that, depending on the parameters that you put. The M, that is the heat transfer coefficient, the length, the perimeter, etc. So you should be able to generate that family of curves for different fins. Okay? So the first thing I do is go into MATLAB and say, okay, you have to search. Okay? So you can search help boundary value problem. It'll point to this particular function, BVP4C. That is the name of the function. You are adding to your knowledge of the various functions. So far we have seen backslash operator, fsolve, fmin search, ODE45. This is probably the last one that we will see in MATLAB, BVP4C. And there's a whole class of programs like that, BVP5C, etc. So BVP simply stands for boundary value problem. 4 stands for the order of the differential equation solver, how accurate it is. 4th order is lower accuracy than 5th order, for example. And C refers for collocation method. It's a method. We are going to see these methods later on. Okay. So that is the name of the function that will solve such problems that we have, like for the fin. Okay. And the help, when you print the help, this is what it says: solve boundary value problems for ODEs by collocation. There will be certain things that you don't understand because you haven't seen what collocation method is, but at this stage you don't care what method they use. All you want is formulate the problem, get the solution. As a process engineer, you want to analyze the process. Okay? You want to ask the question, what would happen to the profile if I increase the heat transfer coefficient or increase the thermal conductivity? What material should I make my fin out of? These are the issues that you want to focus on. Okay? So if you come across things like this, you should be able to kind of ignore. Okay, it's a method. Okay, I'm not in the business of developing these methods. I'm in the business of using it to solve. But what you need to understand is whatever I have shown in red. Okay, what are the things I have shown in red? ODE fun is the name of the function that you are going to write that defines these function f1, f2 in this particular case. BC fun is another function that you are going to write that calculates the boundary conditions. It's going to be a function that will take certain inputs and return outputs. So a function is basically a rule that takes certain inputs and returns certain outputs. In the case of ODE fun, it's going to take y1 and y2 as input and return f1 and f2 as output to BVP4C. And then BVP4C will use that to construct the curve for you. And when it reaches the boundaries, it needs to ask your function by sending the two values for y1 and y2 at the left boundary and at the right boundary. So we need to understand what are the inputs for ODE fun, what are the inputs for BC fun. And then the third argument is, it's called SOLINIT. That's one of the problems. The variable names are very cryptic, right? So this basically stands for solution initial condition. So if it is a nonlinear problem particularly, you need to give some graph like this that may be a good initial guess. We've seen that also in fsolve, fmin search, etc. To get MATLAB going, you need to give some curve. And the initial guess that you may give is assume all the temperature to be 1. MATLAB will be happy with it. Okay? So it will take that and then it will try to deform that function in such a way it satisfies your your differential equation and your boundary conditions. So the third argument is some initial profile. So we need to see how to build all these three. Then it integrates a system, not just one ordinary differential equation, a system of differential equations of the form y prime equals f of xy. That's why we needed to convert a higher order system into a first order system, because this says the y prime is the first derivative. So on the left-hand side, you must have only the first derivative, but you can have many variables. You can have dy1 dt, dy2 dt, etc. Okay, or x in this case. And f can contain as input. So this is again an important interpretation for you, because this tells you that ODE fun must take two inputs. The first one would be x, that is the independent variable. In our case, it's going to be psi. Okay, so that is the independent variable that you see here. Oh my God, I completely erased it. That's not a good color to use. Okay, so that one matches with that one. The second one, y is going to be a vector. So x is going to be a scalar, and it says that. Okay, x on the interval a to b. So this is a general routine, right? So a and b could be anywhere. But in our particular problem, what is a? The interval says, what is the interval between the left boundary and the right boundary? 0 and 1. A would be 0, B would be 1. This mapping you should be able to do. Okay, for your problem, what is the information and how do you map it into what MATLAB expects? Okay, so x is the same as psi, that is the independent variable. Y is the dependent variable. In our case, there are two vectors, y1 and y2. And f is the function that we have already figured out. So we need to write that ODE fun that will implement these two functions. And once you see the function, you will see that it is really trivial. But if you haven't seen it, you're going to sit in front of the computer and say, how do I write that? I know many of you have trouble with that. And initially that is normal. Okay? But as you see examples of this, you should be able to pick up from that. And then you will become comfortable doing a second problem or a third problem. So it's subject to a 2-point boundary condition of the form BC, YA, YB equal to 0. That's important to understand because we have it in the form Y1 is equal to 1 and Y2 equal to 0. But what they want is something like a boundary condition equal to 0. That essentially what they are saying is, rewrite this boundary condition as Y1 at psi equal to 0 minus 1 is equal to 0. Move everything else to the left-hand side. Okay? And that is going to be my first boundary condition. And the second boundary condition, so the boundary condition will take two inputs also. Okay? There is a vector y, which will contain both y1 and y2 at A, and a vector y, y1 and y2 at B. So these four numbers will come from BVP4C. That is, MATLAB will send these four numbers to your function that you're going to write for this part. Okay, you're going to write that part. And as an argument, MATLAB will send these four numbers, y1, y2 on the left boundary, y1, y2 on the right boundary. Then you need to pick the elements that you need and calculate these two functions. So the second function is simply going to be y2 at psi equal to 1 is 0. So you need to rewrite them and send those two functions back to MATLAB. Are you guys with me so far? How many of you are lost? Don't be shy to put up your hand.
We need to write this separately. We can't just specify it.
We need to write two two function files. Okay, and the first function, because MATLAB will call them with different names, we need to identify the name of the function that calculates F1, F2, and returns. And then MATLAB has to know the name of another function that will return only the boundary condition.
Okay, so you have to write a function for the boundary condition.
You have to write a function for the boundary condition, and those boundary conditions must be written in such a way that it is what they call the residual, the difference between the left-hand side and right-hand side. And normally it won't be 0 when you give any arbitrary guess, but MATLAB will take care of driving it to 0, just like it did with FSOLVE. Sorry.
If we had an equation like the third order
Third
that
order.
we said earlier, we need to do. Would there be three conditions in the BC, but it would be a different program or whatever?
It will be a program called BC Fun or whatever you want to call it, but it will have three inputs on the left side and three inputs on the right side. Y1, Y2, Y3 at A, Y1, Y2, Y3 at B, and you will use them to calculate three conditions and return that.
It also recognize that though?
It will automatically recognize it because it can always find the length of a vector. From that it knows how many equations you are solving and so how many boundary conditions you need. Good question. That is what I want you to be thinking. Like, how do I it's a good way to know or test yourself in your mind. I'll get to you soon, okay? That you have understood the concept. Okay, if this is right, if I understand this right, how would I apply it to the other problem that we have seen? By going through the thought process in your mind, I think you will understand. Okay, that's a good question. Now,
so if we use equations, our equations are somewhere to the top where we have to move the right-hand side to the left.
Yeah.
Do we need to put parentheses around the y, like ya? If it's ya minus 1, do we need to put parentheses around all that?
No, you don't need to, because the precedence ordering will work in the MATLAB context. But if you want to explicitly clarify it for your own reading, you can put parentheses to clarify an expression. But MATLAB just requires and applies uniformly precedence ordering in every line that it evaluates. Questions? So what I've gone through so far is how to read the help file and try to decipher a little bit of information. Okay? Now let's go and see how to set up the problem. Okay? And how to solve this. So I have a problem called drFin. I'm going to introduce a few more advanced concepts. Okay, so far, and it is probably a good way for you to work throughout this course. Whenever we write a function file, we put it in a separate file. Okay, each function file has a name, and MATLAB, when you type a name of the function in the MATLAB command window, it searches the path, the current directory and its entire path, searching for that string and see if there is a variable defined or whether it's a function that is defined. But MATLAB, in a more recent edition, has something called sub-functions. That is, function within a function. Okay? And if that function that you are going to write is only called by the driver, then you don't have to put this in a separate file. You can put it in the same file. But that name will be appearing only in the driver function that you are calling. So if you go and type in MATLAB fin, MATLAB will look for a file name with fin. It won't find it. But this is stored in dr_fin. Okay, this entire file name is dr_fin that you see here. So if I type that, MATLAB finds a file and then it goes and executes. But as it executes, if it comes across another function, fin, if it finds that function defined within the same file, it is happy with it. Okay? So it basically allows you to structure the programs in a better way. If you are writing a lot of little functions that are used only for that problem, you don't have to create a separate file. Okay? So that is called a subfunction. This is called a subfunction, and this is called a subfunction. And we will set up the loop tracing so that you understand how the interaction takes place between BVP4C and these. First, I want you to go through each one of those lines and make sure that we understand what each one is doing. Okay? So the first function that you see on the top is the driver. Okay? So all I need to do is to execute that dr_fin in the MATLAB command window, or I can use the green button here to start the execution. It does that function, does it take any inputs? How do you answer the question? Is there a parenthesis after fin? If I have a parenthesis after fin, that means I need to define that input. So this function is basically a driver function, so it doesn't require any input. Does it produce any output? It produces an output called SOL. That's going to contain the solution. Then we will be able to plot it outside if you want in the workspace. Okay? So that is the first line, declaring the function and without any input but with one output. I'm calling it as fin. To execute that function from the command window, I need to type drFin. Okay. So if I type fin, what should I get? Error. Fin is not a file. It's searching for a file, and if you look at all the M files on the left side, there is no function, no file with fin.m. But fin is a function. It's called a subfunction that is defined within that file.
So,
yeah.
If you run that file, and then it comes up with that store fin, you type in fin. So if you run the file,
yeah,
and then store file fin. So if you type fin after you've run it,
yeah,
then it will.
Then it'll know. Then it'll know. Okay. So Did everybody understand the question? Yeah? No? Once I execute that function and set up a breakpoint and see at that stage, does it know about fin or does it know about fin BC? At that stage, it should know about it once it gets into that file. But to get into that file, I need to enter the function dr underscore fin. Okay? Without any input, because it doesn't ask for any input. And the transfer is controlled to that file, and I set up a breakpoint in the very first line. Okay? Remember, I need to call BVP4C and pass it the name of the function, the name of the boundary condition, and some initial condition. Okay? What is the initial profile, the temperature profile? And the initial temperature profile is created by another function called BVP-INIT, and that takes two inputs. Okay? And the first input is the range of the independent variable. In this case, the independent variable goes from 0 to 1. Okay? So if you see here, that variable, come on. Okay? That variable is going from 0 to 1 in steps of 0.1. Okay? So it says construct a set of points between 0 and 1 in steps of 0.1 and solve it for only at those positions on the independent axis, x-axis. So that represents psi. Okay? The second variable is the initial guess along all those points for the two variables, that is y1 and y2. So what I'm trying to do conceptually is the following. Okay? I have my domain as psi going from 0 to 1. In BVP-INIT, I'm saying y1 is 1. And this is y1, the initial guess for y1. And y2 is 0 everywhere. And I've constructed 10 points. I'm saying, give me the solutions only at those 10 points. Okay? So the data points will come only at those. So I'm specifying my initial guess as 1 for y1 and 0 for y2. That is the second variable. So these are just two numbers, but they are taken and distributed throughout. Everything is a constant. Theta 1 is a constant, theta is a constant, and d theta d psi is a constant. That's what we are saying. Okay? Now, is that right? Obviously not. It's not going to satisfy the differential equation or the boundary condition. So when I execute that, I'm going to have that variable sol INIT defined. Okay? So I can print it out. Let's just do that and see sol INIT. Another big stumbling block. What does that mean? Is it a variable? So we are going to be introduced to something called structures. Okay? Now, we have seen a scalar variable, a equal to 1. We have seen a vector, a equal to 1, 2, 3, 4. We have seen a matrix. These are all different types of variables, different data structures. Okay? So the structure is the next level of complication. So it simply says sol INIT, for example, structure is it has two arrays in it, embedded. The first array is X, which is the location of all the independent variables. And the second array is Y, which has two columns, okay, Y1 and Y2 at the same locations. So to print that, all you need to do is sol INIT dot X. Okay, just a variable, but dot X means give me the X component of that structure, and it prints out the independent variable from 0 to 1 in steps of 0.1. Okay, if you do sol INIT dot Y, it prints out two rows. The first row is for Y1, the second row is for Y2. Those are the initial conditions. Okay, so a structure is nothing but a variable dot another variable, and in that you can pack many variables into one variable called SOLINIT. When it returns the solution, it's also going to return in a structure. Okay, the reason why you introduce structure is to keep things simple in terms of writing, but conceptually it does pack more information into the same. You still have one variable SOL coming out, but it has many information packed into that. Okay, so Any questions on the structures? This is the first introduction. Have you seen structures before in your other previous computing course? Not yet. This is your first introduction to structures. We will play with them and learn as we go along. Okay? So what is going to happen now is the control is going to be passed to BVP4C. Okay? And BVP4C is going to call fin many times, passing each time the current location of x and y1 and y2 in the vector, second vector. And then it will get back the two functions, and it will do something with those functions to construct the solution. And it will also make call to fin BC, that is this function. Okay, and it will send two vectors, y1, y2 at the left position, what they call A, and y1, y2 at the right position, what they call B. And you will use that to send back the two functions. So what you must recognize in these two functions is the two functions that we wrote down on a piece of paper. What is F1 and what is F2? That goes into this function. And what is YA1 minus 1 and YB1? Okay, these are the two boundary conditions that we wrote. The crux of the problem is in those three lines. The rest are all setting up communication between BVP4C and these two functions. One of the questions that you asked, I guess, is does it know about fin now? Because we are inside the scope of the main function. Okay, so it must know fin. I really don't know the answer to that. Since you asked the question, let's find out whether it knows about fin now. Type fin. It still doesn't know. Okay, so I'm learning something. So the fin is a local function, sub-function within that, but once it executes that, perhaps it will automatically come. If I set a breakpoint here, and then ask it to continue. So what happened at that click is the control was transferred to BVP4C, and BVP4C got the name of the two functions, and it sent the control to the fin function with certain values for x and y. You can interrogate what those values are. For example, if you place x, so it's saying at x equal to 0, what is the left boundary? Y should have two numbers, y1 and y2. So if x is 0 and y1 is 1, y2 is 0, what are the two function values? Return those to me. Okay? And it's your job to define. So I just made up some parameters. Heat transfer coefficient 0.5, perimeter 1, length of the fin 1.5, thermal conductivity is 1. So from that, I'm calculating this number, dimensionless number m. And that m goes into here. It's used here. Now the y2 comes from BVP4C, right? So y2 is 0 in this case. You can see that is 0. So that is what will be used here. And y1 is 1. And you can calculate what m is. It is calculated m to be 2.25. So if I execute these, now it is ready to go out. Where does it go out? Back to BVP4C. That's where they came from, right? So we'll go back to that. But it will carry with it these two values for functions, F1 and F2, 0 and 2.25. It will carry this back, okay? And then the interaction between BVP4C and fin takes place many times, okay? So it comes back. Let's set up a breakpoint in the boundary condition and remove this and see when does it come to the boundary condition. There it is. So BVP4C communicates with both these functions. Okay, now it has called this function, sent it certain values, okay, for y1 and y2 at the left boundary, 1 and 0, 1 and 0. And then it asks what is the residual, what is the error in the boundary condition equation. It's 1 and 0. Now, you need to understand this because the F1 and F2 that we put on the right hand side is what we developed. Similarly, the boundary condition that you see here is YA1 minus 1. Okay, where does it appear in that equation? Where is that? I'm trying to go to the boundary condition. See, here it is. Y1 minus 1. That is the first equation for the boundary condition. and it is at psi equal to 0. So if it is psi equal to 0, you call it as YA. If it is at psi equal to 1, you will call it as YB in MATLAB's terminology. Okay? So Y2 at B is 0, and Y1 at A minus 1 is equal to 0. And that's what we are inputting in this function. Okay? YA at 1, the first index, minus 1, whatever that number happens to be. MATLAB will drive that to 0. Okay? And similarly, YB at 1. YB is the right boundary condition, and it's the first element of the two vectors Y1 and Y2. So the index refers to the element number, first unknown or the second unknown. A refers to the left side, B refers to the right side. And only when you do a problem by yourself on this, you will understand it in your mind. Okay? So this is just introducing you how to set it up. You may have to listen to this again as you are doing it. Any questions? So if you can set up these two functions, then you are set to solve this problem. So I can remove this breakpoint, and I'll set a breakpoint here, and then continue execution. So I have gotten the solution from BVP4C, okay, for this particular problem. Where is the solution saved? It's saved in SOL. SOL is a structure. Okay, so if I go to the workspace and ask what is SOL, it will say it is a structure. The structure is, that structure simply means many arrays packed into one variable. Okay, and instead of using the array number like in a simple array, you use a different variable. So sol.x will give you the x variable. Sol.y will give you the y variable, y1, which is our solution. Sol.yp will give you the y prime, the derivative, that is y2. Okay, so let me just do that. Sol.x. What do you expect to get when you type this? These are the x locations where I wanted the solution. I packed that in BVP INIT. And then if I say y, that is really the solution that I want. Okay? And yp is the derivative solution. So in order to plot this, you need to understand that so that you can construct your plot line correctly. Okay? So the plot command takes an x-axis and the y-axis and plots one against the other. Okay? So here I'm saying on the x-axis, plot sol.x. That is, from the structure, take the x-axis, plot it on the x. And then sol.y1, the first variable, and plot it with a symbol and a dot. So when I execute this, I get my graph. And there it is. That is the temperature profile along the fin. Obviously it is 1, as we said in the boundary condition on the left-hand side. It is 0 on the right-hand side. Okay? And the profile looks something like this. These are discrete temperature values at value of 0.1, 0.2, 0.3. Okay? If you want to get more accurate result, what do you need to do? If you want to get the temperature profile at more points, if I give you this program and I give you only one task, okay, get me the temperature profile not only at 0.1, 0.2, but 0.05, 0.1, 0.15. Very good. Change the interval. So here you go back and change that to 0.05 and save that and run it. And did it work? Yeah, I guess not. Pardon me?
You have a breaker.
I have a break. Thank you. Maybe I'm wasting your time. You guys follow better than me. Okay, I have a break, so it hasn't plotted, updated the plot. I'm still looking at the previous plot. Very good. There you have. Okay. So the best way to learn these things is I will put all these codes onto Moodle also. Okay. So you can take these codes. Yesterday tutorial also, I'm preparing them for uploading it. So take those codes and run it and change it and see how it changes the problem. Okay, any questions? Yeah.
With the NBC, that res, does that mean anything, or is that specified in the help?
Well, the res is a variable name that you give, which is abbreviation for residual, but it could be anything that you want. But what is important is you have to calculate that because that is the only one that's going to be sent back. So if I call this F, that'll work. Okay? So it's just the difference between the left-hand side and right-hand side. That's how we have to write the boundary condition.
And just the Y and the YB have to be specified like that?
Yeah. Yeah. Okay.
And when you write Y and YB, it knows that it's the left and the right automatically.
A is always the left, B is always the right. Yeah. Yeah. That's why it sends in two numbers, YA and YB. Okay? And each variable YA and YB will contain two elements in the array because we are solving a second order problem. If it is a third order problem, YA will contain three numbers, YB will contain three numbers for the right hand side. Those will be Y1, Y2, Y3, etc. Okay, any other questions? Okay. Here is a profile. Now let's be chemical engineer. So far we have been computer people solving the problem. Now we are chemical engineers. Okay. The question is, if I increase the heat transfer coefficient, how would the profile change? I'm increasing H. For this, you need to understand the mechanisms that we talked about. Okay. If I'm increasing the heat transfer coefficient, what does the heat transfer coefficient do? It controls how fast heat is removed from the fin surface to the surrounding. So if I'm removing that heat very quickly, what would happen to the profile, the temperature profile? That is the question. Okay. So if you go back to this picture, there are two mechanisms we talked about. K increases the rate at which this is being transferred this way, and H increases the heat transfer to the surrounding. So if I keep K constant, but construct a whole series of solutions, and in reality what you will do is you will have a fan. On CPU, for example, you have a fan, and you increase the speed of the fan. That means you are removing more heat through this mechanism. So you are increasing H in a sense. Okay. My question to you is, if I increase H, do you expect the profile, we get a profile like this now. Okay. This is for a certain value of H equals 0.5. If I increase it to 2, 4, 8, do you expect it to go this way, or do you expect it to go this way? What do you expect? Lower and to the left, right? Because you are removing the heat, that means the fin should cool. Right? If you're removing the heat faster, the fin should cool, so the temperature should go below this. Okay? Now let's see whether that happens. How do I do that? I give you this piece of code, and I say do it for H equals 2. What will you do? Just go and change it as here, and then save it and run it again. Right? Let me not make the same mistake again. And you do see that coming down. Right? So this is a process engineer now in you that says, okay, how is the process affected as I keep changing the environment, the parameters, the process parameters in the model? Now I ask you to generate a whole series of plots for different values of H. H equals 0.5, 1, 2, 4, 8, etc. And I want all the graphs on the same plot so that I can see how does the temperature profile change. The problem remains the same. Okay, so this function essentially remains the same. I need to change H to a series of values. This is a problem that you have encountered, and some of you have creatively solved it in your current assignment. For example, I ask you to do for two areas. Okay, so one way is go and change the area once, run it, and then go and change the area again, run it. But you don't get both the results in the same run. So I want to get all the plots in the same run. So how do I do that? Okay, so you are learning how to improve on the MATLAB function that we have. And what I'm going to do, I'm going to show you the difference between local and global variables that we talked about earlier. How I can use that to change the value of H inside that function from outside. Okay, so I need to put, immediately I should recognize, I need to put a loop. The loop around what? Loop around line 3 and 4. Because line 3 solves it, line 4 plots it. Okay, so I need a loop around 3 and 4. How many times do I put the loop? As many H I want. So I create a vector H for heat transfer coefficient, maybe 5 numbers. So I want to solve for 5 cases. And I want to set up the value of h in the calling function and ask it to be picked up in the fin function automatically. Okay, how do I do that? Using something called a global function. Okay, so here I have, to save time, I have already pre-built that. So let me close that. So it is essentially the same function, but what I did was, in the second line, I declared h, the heat transfer coefficient, as global. What that means is, if I set the value there, it will be picked up by all the other functions. Otherwise, the variables are local to a function. But by declaring a variable specifically as global, I say, okay, this value is going to be picked up from all the other functions as well. It is globally available. So that's a declaration statement to global h. And then the third line is the same as we had before. The fourth line is one where I set how many heat transfer coefficients I want to solve for. So I create a variable called capital H with an array, and it says 0.1, 1, 3, 5, 8. I want solutions, I want curves for these 5 values of the heat transfer coefficient. Okay, no, I need to set up a loop. Okay, so I said n is equal to length of h. What am I doing there? Counting how many heat transfer coefficients I have to solve for. Then I put a hold. Do you remember what a hold does? Cannot afford to forget. Hold holds the plot as you add more graphs to it, because I want to add all the graphs onto the same plot. So hold simply keeps the plot frozen so that I can keep on generating additional curves on the same graph. Then I set up the loop for I equals 1 to n. N is going to be as many numbers that I have in h. And what I do is extract, but when I equal to 1, I extract the first value 0.1 and put it into lowercase h. Lowercase h is the global one. So that value of h will be picked up in any other function where I declare the same variable to be global. So in this function, I also declare h to be global. So the value will automatically be picked up, the value of 0.1 the first time, 1 the second time, 3 the third time, etc. Okay, and I got rid of h because I'm not setting h equal to a number here. So I got rid of that line that had h in it. So this is how I pass the value from one function to another function without passing it as an argument, as a global variable. Any questions on the concept? Do you understand the concept? Okay, the rest of the functions are all the same as before. But I put up a loop and I'm going to run through this several times. So let me set up a breakpoint and start executing this. Why is it not? Okay, so I'm calling from the main driver function, and I have set up 5 values for capital H. So I'm going to get a graph with 5 curves. Okay, and what is the first time? The value of lowercase h is the heat transfer coefficient that is being passed here. So it's going to come with a value of 0.1. It is 0.1 there. Remember, I'm not passing it through this. But still, when I come and ask what is the value of h, it will automatically be the same value. It will be passed. Okay? So we can check that by simply setting up a breakpoint here and say continue. So now I am in the fin function, and I say what is h? 0.1. Okay? And let me remove that. So let me step or continue. Okay? Now I have solved the problem for 0.1 with h equal to 0.1. And the solution is saved in the structure SOL. And the graph looks like that. Okay, so because I put a hold, I also have the previous one. But when h is equal to 0.1, that is the temperature profile. Okay, and let's keep that open if possible, and then keep running, stepping through this. Okay, so I run again. Now I is going to be 2. I is 3 already, okay. And h is going to be 3. So I guess I must have done it twice. So it is picking up the third value from the array h and setting it equal to the lowercase h, which is what is being picked up here in calculating h. Okay. And if I do this, I get one more graph. One more graph. One more graph. Okay, so you can see clearly as you increase the heat transfer mechanism by increasing the fan speed, you are bringing the temperature down very rapidly. So the tip of the fin is going to be much cooler. Okay, then when you have higher, lower value of heat transfer coefficient. So this one is for 8. The last one is for H of 8. The first one is for H of 0.1. So this gives you the tool as a process engineer to analyze problems for varying operating conditions. Any question on this code? Okay, hopefully at the end of this course you will have at least these codes that you can look at and then build, using these as examples, build other problems that you want to solve. And if you continue this, I think you will just get the labels and all that. That's what we are putting, the title, the label, and everything on that. Okay, that's basically how you solve boundary value problems. Okay, I have another example. Let me see where I can find it. Now the question is, we know how, let me ask you, let me pose these questions for you to think about. I have solved this problem when the boundary condition is given as theta equal to 1 on the left side, theta equal to 0 on the right side. Okay. Now I say, remember we talked about two alternate specifications. So we have solved for this. If temperature is 1 at the left side, 0 on the right side, we saw a whole series of solutions. What would happen if I drop this boundary condition and say the boundary condition is not, the tip is at room temperature, but the boundary condition is what you call the insulated boundary condition. There is no heat transfer from the tip. So its derivative is 0. What do you think will happen to theta at that end? Again, it's a process engineering question. How would you expect the profile to change when I change the boundary condition at the right? And then the next question is, how do I change that code? If I give you the code and say, go and solve for this problem, what will you change? These are the two questions we need to answer. So
we went from changing it from theta equals 0 at the right hand side to the derivative of theta equals 0?
Exactly. You can take wild guesses, okay? And then we will reason it out, see whether it makes sense or not. Anybody want to come and sketch the graph? Oops. Psi 0 to 1. What should the profile have as a feature on the right side? The derivative is 0, right? So on the left side, it must start here, so it must go down. On the right side, it must have exactly, it must have a horizontal slope. So it could be like this, it could be like this, it could be like this. Okay, all these are possible.
Could it be a straight line?
It cannot be it could be this.
Yeah.
That's possible. Okay, that would satisfy. When would that happen? That's an extreme limit.
It's the same temperature as surrounding.
It's the same temperature everywhere. That means you make H equal to 0. That is, you're not taking any heat out, and you're putting heat from the left, so it's going to heat the entire fin to the same temperature as the base, and nothing escapes. Right? And that's possible. That's possible. But it must satisfy on the right side. If you take the derivative, in all these cases, the derivative must be 0. On the left side, the function must have a value of 1. So these are all the possible type of sketches that are possible solutions. What that means is, if I touch the tip of the fin, it could be hot. Okay? So if the heat transfer coefficient is low, you could have a temperature that is not 0. But if the heat transfer coefficient is still high, you could have this, meaning the tip is still 0, but its derivative is also 0. Okay? So this is the direction of increasing H. Sorry, decreasing H, right? Yeah, decreasing H. As you increase, it should go this way. So decreasing. Do you understand conceptually what you expect? That's very important to do, because when you're doing a programming, if you get an answer you should be able to see whether it makes sense. Does it make sense physically? This is what I would expect. Okay? At least qualitatively, if it is right, then you can say, now I can check quantitatively what to do. So we have answered the first question of, if I change the boundary condition, what kind of profile I would expect. The second question is, okay, how do I change the program to implement this boundary condition on the outside? What do you think I should do? Let me put up the program. So I'm going to give you this function, this file that has several cases for heat transfer coefficient, and I want you to change anything that you want in this such that this problem will be solved. What will you change? Does the equation change?
Boundary condition.
Which boundary condition? Where? Exactly. I'm impressed. But all of you, are you following? What I want is dy d psi. What is dy d psi? That is same as y2. Okay? Remember, ya and yb in the boundary condition functions are for the left and the right. So yb will come with two numbers. Okay? So it is b that you want to manipulate because it is on the right hand side. And it is not y1, that is, it is y2 that you want to manipulate. Okay? And in an exam, I might do this. I might give you a code and say, change one thing. That will solve that particular problem. So you should be, I'm not going to ask you to write a code, but take a code and identify how to implement, how to change. So in here, who said that? Very good. What would you change? Which line would you change? What would you change there?
The line 31.
Yeah.
I would make that 1 and 2.
-1?
Make the 1 and 2.
Make her 1 and 2.
Why? Is that like that?
Yeah.
No. Okay.
Y,
You would change YB because it is on the right hand side, and you would set that equal to 2. The array is 2, the second element. Y2 stands for d theta d psi. And you want d theta d psi to be equal to 0. Okay? So you want y2 to be equal to 0. The first element is still y1, that is on the left side. You want theta to be equal to 1. So that is theta minus 1 should be equal to 0. Remember, you have to write it as left hand side minus right hand side. So with that one change, if you know what to do, it doesn't take very long in an exam. Just a few seconds, right? But it is very important to know where to change and what to change. Now if I solve this, save this, and run this program, let me does it have the slope 0? You can see that it comes down, and if you take the derivative of draw a tangent, the tangent should be 0. Okay, so that is for h is equal to 0.1. Okay, so continue. I guess somehow I didn't execute the hold. Okay, I just wanted to run this again so that the hold is executed. Okay. All right. There. Okay. So that the first curve is for h equals 0.1. Okay. That means you are removing very little heat, so the fin gets very hot at the exit. So what does it mean when I say theta equals 0.8? Suppose I give you this problem. Theta is 0.8 and T infinity is 200 and T0 is 200 and T infinity is 25. Find out the temperature. How would you answer that question? You have a solution. This is a graph which says when the heat transfer coefficient is 0.1, the dimensionless temperature is 0.85. Okay, from this graph you get that. And then I ask you to calculate the dimensional temperature. What is the real temperature in the fin? How would you do that? Do you understand the question? Exactly. You're on the right track. Okay. So the question that I'm asking is, if I give you that theta is equal to 0.85, there is a profile is like this, and for h is equal to 0.1, second boundary condition, and theta is 0.85, what is the real temperature if T0 is 200 degrees and T infinity is 25 degrees? What is the real temperature? All you have to do is use the definition for theta. Theta is T minus T infinity divided by T0 minus T infinity. But you know that to be equal to 0.85. So here you know T infinity, you know T0, so solve for T. So as you pointed out, all you need to do is write it as T is equal to T infinity plus 0.85 multiplied by T0 minus T infinity. Okay, that is 200 minus 25. So it's going to be 25 plus 0.85, that is 85% of the difference, 175. Whatever number that comes out to be. Okay, that's how you will go back to dimensional temperatures that you are solving for after you get the temperature in the dimensionless field. Okay, so let's complete this. So it's done. Okay, and you see all cases that we talked about. Yeah, sorry.
Also, when you set the boundary conditions and you said YB is 2 equals 0, how does it know that what you're, because if you didn't define like a vector Y anywhere, how does it know what you're defining as 0? Is it just built into the function?
Yeah, well, the question I think is, how does it know that I have only two variables? How does it know y2 is for the derivative, right? That's what you're asking. Very good. So it knows that by simply when it calls, like here, this is the first place it will know what is the number of equations we are solving. Because in the initial condition, SOLINIT, I'm passing a vector of 2. I'm saying y1 is 1 everywhere and y2 is 0 everywhere. So it counts the length of that and it says, oh, you're solving a two-dimensional problem, two equations. Okay? Then it's going to treat y1 as the variable, y2 as its derivative. Okay? And when it sends y, it will send two numbers, as we saw within that. And it will do the same thing for the boundary condition. When it sends ya, it will send two numbers in that location, ya. So the a refers to the left side, and 1 and 2 are the function and the derivative. Similarly, yb, b refers to the right boundary condition, 1 is for the temperature, 2 is for the derivative. And that is why we picked 2 for the derivative and b for the right side. Okay, that you should be able to do, because in an exam, this is minimum I would expect. I'll give you a problem like this, I will change the boundary conditions. Instead of saying that the left-hand side theta is 1, I will say the left-hand side the derivative is something, and the right-hand side temperature is different. And how do you change these things? How do you set up the problem? If you understand that, I know that you can translate your problem into MATLAB. If somebody gives you the structure, the framework of the code, you can just at least change it and get solutions. Minimum, you should be able to do that. It'll be great if you can write your own code. Yeah.
One of our boundary conditions was like at 0.5, which is still how do you
remember, this is what they call 2-point boundary value problem. There can be only 2 points where you can specify. Okay, so it has to be, your domain can range only from 0 to 0.5. Okay, instead of 0 to 1, x going from 0 to 1, you can go from 0 to 0.5. And you can specify the conditions at 0.5. Question then is, how do I tell what is the x range to the problem? Right? Where in the code am I telling that I need to solve this for x or the independent variable going from 0 to 1? Where did I do that? Again, it's on BDP INIT. So if I change that 1 to 0.5, then it says solve from 0 to 0.5. So it will apply all the right boundary conditions that you specify B at that location, 0.5.
So if you're third boundary condition, it would have to be
if you have a third boundary condition,
you have your extra bit of information has to be one.
it could be, yeah, it could be mixed some of the conditions should appear on the right, some should appear on the left. The total number of conditions that you have should match the order of the differential equation. Okay, so if I have a third order differential equation, I will come and say 0. That means it expects third order equation. So that will not work with this function anymore, because when it sends 3 numbers, it expects 3 numbers back. So I need to define the third equation here. I defined first and second. I need to define the third equation. Okay? Does it make sense or no? Any other questions? Okay, I think in terms of theory, we have gone a bit faster than what you're doing in your assignment. So we need to kind of sync the two. The next assignment is going to be on ODE initial value problem with some problems, simple problems from exam point of view. And then another week after that, you'll get a boundary value problem. So don't forget what we have talked about until then. All right. Okay. Yes,